And so last time we were talking about the parity operator. Which we represent with a capital letter pi. And so in the active view, what this thing does is if we act on a position eigenstate, it gives us back an eigenstate of position, but with the opposite value of x. And it does the same thing for momentum. So if we act on a momentum eigenstate, we get back the opposite momentum eigenstate. Okay, on wave functions, it follows from that its representation on wave functions is that if you act on a wave function psi of x, you get back psi of minus x. And if you act with a momentum space wave function, psi tilde of p, you get back psi tilde of minus p. So those are the representations on wave functions. And then finally, there's the passive view operation. That is, what does it do to operators? And so one thing it does is if you do pi x pi, normally for a transformation, the first pi would be daggered, but pi dagger is equal to pi. So this is unitary and Hermitian. Which makes it easy. You can't forget the dagger because it doesn't do anything. Okay, so pi x pi is negative x, and pi p pi is negative p. So it flips the sign of both position and momentum. And so more generally than that, you can talk about what it does, not just to position eigenstates and position operators, but any state and any operator. And so for states, it may happen that pi acting on a state gives you back an eigenvalue. I'll call it little pi sub psi times the same state. Okay, and the eigenvalue we proved had to be plus or minus 1. But of course, not every state is an eigenstate of parity. So it has to be special states psi that obey this. And similarly for operators, it may happen for an operator A that pi a pi is equal to either plus or minus 1 times A. So again, I'm going to call the number that goes there pi sub A. And if pi sub A is plus 1, then it's said to be even. If pi sub A is minus 1, then the operator is said to be odd under parity. And again, not every operator will be either even or odd. There are some operators that are just neither one of those. Okay, now a special situation arises if the Hamiltonian is even. So examples of that, we've seen some examples already. The free particle has a Hamiltonian h equals p squared over twice the mass, and that is even. Okay, because the p flips sign, but there's a square of it, so it flips sign twice. Okay, a particle in a square well is an even Hamiltonian. So centered at x equals 0. That part's important because there are some books that actually treat the square well or the particle in a box with one edge at x equals 0 and the other edge off to the side. That would not be invariant under parity because it's not centered. Okay, and so that's why we chose to choose the center of the box at x equals 0. We haven't done it yet, but following the midterm, we will launch into the harmonic oscillator. Again, if it's centered at 0, namely if it's Hamiltonian, looks like this: p squared over 2m plus 1/2 m a frequency omega squared times x squared. So both terms, again, if you act with parity, flip sign twice, p flip sign, x flip sign, but they're both to the second power. So that would be an example, again, of invariant under parity. And here's one that wouldn't be, is suppose I had p squared over 2m, so far so good, but then I had a term linear in x, and then maybe a term quadratic in x. So now the linear in term in x spoils everything, and so this would be not invariant under parity. Okay, but if it is invariant under parity, then if h is even, that's the same thing as invariant under parity, then it follows that parity commutes with the Hamiltonian. That's just rewriting the condition. And so they are compatible operators. Okay, and compatible operators means you can find common eigenvalues for them. So for example, in the free particle, we've already talked about what the common eigenvalues are. So let me divide this into even here and odd. This will be 2 columns. So for the free particle, you can write the even states as 1 over the square root of 2 times a momentum eigenstate plus the opposite momentum eigenstate. And the odd one will be 1 over square root of 2 p minus p. Okay, so the point is, the reason we have to write it this way, if we're writing in terms of momentum eigenstates, is that parity commutes with the Hamiltonian, but it does not commute with momentum. And that's why these things are linear combinations of momentum eigenstates rather than being momentum eigenstates. For the square well, or its subsidiary case, the particle in a box, then we wrote things in terms of energy eigenstates, and the even states turn out to be the ones with odd integer n, the way we defined things, and the odd states turn out to be the ones with even integer n. Okay, and when we do the harmonic oscillator, it's going to turn out to be the opposite. We're going to label our energy eigenstates by n again, integers, but the ones with n equals even are the even states, and the one with n equals odd are the odd states. So you can't tell just from what the label is, whether even if it's some integer that's even or odd, you can't tell necessarily from that whether the state itself is even or odd. And the reason we write them this way is, again, because the parity operator commutes with the Hamiltonian. So anything that's an eigenstate of the Hamiltonian, if it's non-degenerate, which it always is in one dimension for a bound state, is also automatically a parity eigenstate.
Professor, I have a quick question.
Yeah, sure.
Just to clarify, why did you say that the parity and the Hamiltonian they can commute? Is it because they're, whenever the Hamiltonian's even, it's in the parity operator's invariant, was it?
So it goes back to so let me rewrite it here. Okay, so this is the statement. Oops. This is the statement that the Hamiltonian is even under parity. Okay. So let's assume the Hamiltonian is even under parity, as it is in those 3 examples I mentioned. And now I can just act with pi on both sides. Okay, and pi is equal to the identity operator. So from this equation, we get that Hamiltonian pi equals pi Hamiltonian. I should say act on both sides on the left, or from the left. Okay, and this is the statement that they commute. Right, I just rewrite it as h pi minus pi h equals 0. Okay,
Thanks. That clears it up. Appreciate it.
sure. Okay, other questions? All right, so notice if the Hamiltonian is odd under parity, which is very rare because the p squared over 2m part is even. And so you'd sort of have to cancel that out somehow, which is pretty much impossible in the simple examples we're going to be doing anyway. So it doesn't really arise, but if it did arise, nothing particularly special would happen, because that would mean that parity anti-commutes with the Hamiltonian. And then you don't get the nice things like simultaneous eigenstates or anything like that. Okay, so yeah, go ahead.
You said no, down. You said
Okay.
you act with pi on both sides on the left.
Yeah.
So is it like pi and acting on pi is 1? Is that what you did for the left side?
Yes, pi Hamiltonian pi. This pi is identity.
Oh, okay.
I did that wrong. So this should have been a pi h pi. Pi's and h's are too similar. Okay, and so that gives just Hamiltonian times pi.
Okay, thank you.
Sure. Okay, so let's consider states and operators that obey this sort of rule, these sort of rules right here. So this is going to be one of the most important implications of parity. You could say, why are we bothering to define it? And so it does something very useful, namely it gives us selection rules. So selection rules are ways of telling in advance when something has to vanish. Okay, so suppose that you have an operator A, and it has well-defined parity, which just means that the number pi sub A is either plus or minus 1. Okay, and suppose that you're talking about states, psi and phi, that also have well-defined parity. So these are parity eigenstates. So one way this could happen is if your Hamiltonian is even under parity, and then you classify your energy eigenstates as even or odd under parity. But it could even happen if the Hamiltonian is not even under parity, and your state just happens to be an eigenstate of parity. So these are parity eigenstates with eigenvalues pi psi is plus or minus 1, and pi phi equals plus or minus 1. Okay, then consider the following matrix element, phi a psi. Okay, so the first thing we can do is we can change the A into a pi sub A by putting parity on either side of it. Okay, so there I've just used this fact. Okay, but now I can go ahead and look at this and say, oh, that's pi sub psi acting on psi. And this is going to give pi sub phi acting on the bra phi. And so the whole thing is just a product of these three numbers, pi a, pi phi, pi psi, times the original matrix element. Okay, and so the product of the three parity numbers is either plus 1 or minus 1, because each one of them is plus 1 or minus 1 by assumption. And so if it's -1, then what we're saying is the matrix element here is equal to negative of itself, and the only way that can happen is if it's 0. Okay, so what we've learned is that the matrix element vanishes unless exactly 0 or 2 of the 3 numbers is 1. So unless exactly 0 or 2 of, I'll write it this way, of omega, psi, and phi have odd parity. Okay, so again, we can talk about both operator, I didn't mean omega, I'm switching notation here. I meant A. Okay, so you can talk about both operators and states as having even or odd parity, and if they do all have well-defined parity, then the matrix element vanishes unless the total parity, what you get by multiplying them all together, is even. Okay, so for example, this is a very common situation. We've already even seen it in action. If you take the expectation value of an operator, that's 0 if the operator has odd parity. So the reason we've seen this actually in several examples is X is an operator with odd parity. And if you take its expectation value in any state, whether the state has even parity or odd parity, that matrix element must vanish. And we saw that actually in action by doing an integral. So as a subcase of this, for both the square well and the particle in a box and the harmonic oscillator, which we haven't done yet, so we're anticipating a little bit. If we take an energy eigenstate, n, and ask for the expectation value of x, we're going to get 0. This is for any energy eigenstate, because any energy eigenstate is also a parity eigenstate. And it doesn't matter what its parity is, because there's 2 of them here, and so the parity will cancel out. Okay, and similarly, if we take the expectation value of momentum, we're guaranteed to get 0 if the Hamiltonian commuted with parity. So just to give an even more general example, suppose I consider the operator xj pk to the k. Okay, that has parity -1 to the j plus k power. Okay, and so it's got well-defined parity, and so its expectation value is going to be 0 in any parity eigenstate. So psi x to the j p to the k psi equals 0 if j plus k is odd. And the state that you're evaluating it in has well-defined parity. Okay, and so for both the square well and the harmonic oscillator, the only property of the harmonic oscillator that we're using here is that its Hamiltonian is invariant under parity. That's why it's possible to talk about it without even having done it yet. Okay, that means any matrix element like this. Now I'm doing a matrix element between 2 states that might be different. This equals 0 if n plus m plus j plus k, that's an integer if it's odd. Then that thing will vanish. Okay, so one of the reasons this is very useful is it will save you a lot of work. you can sometimes look at something in advance and saying, oh, that thing has to vanish. I don't have to bother computing it, which is a very useful thing to know. Okay, questions on that? Okay, so the transformations we've talked about so far have been translations and parity. Translations is continuous, parity is discrete. And we will also be talking about time translation and angular momentum. So let me talk about time translation first, because in a way we already have. So time translations is just another kind of unitary translation. And we've already seen that the time translation operator, or the thing that takes a state from one time to the next time, is a unitary operator. So let's say we start with some state, psi, and we're starting at time t0. And so I'm just going to call that state psi sub 0. It's our initial state. And then we ask, what is it at some later time? T0 plus epsilon. And we already know the answer is this. If epsilon is infinitesimal, it's the identity operator minus I epsilon over h bar times the Hamiltonian at the time t0 times the initial state, which was psi 0. So I'm admitting the possibility here that the Hamiltonian depends on time. And so what does this say? This statement is h of t0 is the generator of time translations. Okay, so there's this deep dual role that the Hamiltonian plays. It is both the total energy operator, and it is the thing that generates time translations. But now, suppose we do the same thing, but we start at some different time. We're going to start with the same state, but we're going to start it off at a different time and also evolve it forward in time by epsilon. Okay, so now repeat, but starting at time t1 instead. Then the state at time t1 plus epsilon is going to be identity minus I epsilon over h bar. This time I have to use the Hamiltonian at time t1, but I'm assuming I'm starting with the same initial state, psi 0. Now, let's suppose that if we do these two things, we happen to end up with the same state in the end, which is not always going to be true, but let's suppose it is true. So if, with a big double underlined if, these are the same state, okay, then we take the difference between them. And we see that when we take the difference between them, this is just going to cancel because we're acting on the same thing. And so the difference is just going to be the difference in the Hamiltonians. Okay, and so that means that we need h of t1 to equal h of t0. So the only way they can be the same state is if the Hamiltonians at the two different times are the same. And so that's another way of saying that the Hamiltonian in that case doesn't explicitly depend on time. So notice I'm writing its partial derivative. That means any explicit dependence on t, like if it had some factor that was proportional to t or t squared or something. Okay, and so then the partial derivative would be 0. And then we can plug into Ehrenfest's theorem that we wrote down last time, which said the expectation value of any operator, and here we're using the Hamiltonian as our operator, is equal to the expectation value of the operator commuted with the Hamiltonian plus the partial derivative of the operator in expectation value. But this is clearly 0. The Hamiltonian commutes with itself. And this is clearly 0 from what we just showed. And so this will be 0. Okay, so if your Hamiltonians are the same at two different times, no matter what the times are, then its expectation value will be 0 also. Okay, which makes sense. May not be completely obvious though, but it turns out to be true. Okay, so that was just a comment that time translations are generated by the Hamiltonian operator, and we still have to do angular momentum, and we'll come back and do that later. All right, so let me make one other stray comment that I think I've meant to make earlier but forgot. And one of the reasons for bringing this up is because it's something that's implicit in one of your homework problems that's due on Friday. So this has to do with a special kind of observable. We talked in general terms about what observables are, but this is an observable. And this observable corresponds to the following question that you can ask. So given a state, and just to be specific, we'll call the state psi. What is the probability that you'll find the system in another state? And so we'll call the other state that we're asking the question about, we'll call it phi. So in classical mechanics, this is kind of a silly question. If your particle is located at a specific point with a specific momentum, then it's located at that specific point with that specific momentum. And so there's not really much to talk about. But in quantum mechanics, the idea is that this can have a non-trivial answer even if psi and phi are completely different states. So this is relevant, by the way, to homework 5, problem 2. Okay, and so given the fact that this is a physically sensible question, there should be an observable that corresponds to it. And here is the observable that corresponds to this question. It's just the projection operator for the state phi that we're asking the question about. Okay, so the projection operator, we're going to assume that both states are normalized. If they're not, then you have to go ahead and normalize them. Okay, so the observable in this case is a projection operator. Okay, so just note that this projection operator is Hermitian, which it has to be an observable. Okay, and it's Hermitian because if I take the Hermitian conjugate, it just takes this phi into that phi, and it takes that phi into that phi, and it leaves the whole thing invariant. So the dagger of p phi is equal to p phi. Maybe I should write that down. P phi dagger equals p phi. And let's think about what its eigenvalues are. Because it's a projection operator, its eigenvalues are 1, and then the corresponding eigenstate for that is just nothing other than phi. Okay, and 0. And there the eigenstates, and there are lots of them usually, are all states that are orthogonal to phi. Okay, and so what happens if you measure this observable? You're guaranteed to get either 1 or 0. And if you get 1, then the physical interpretation of that is, yes, we are in the state phi. even though you didn't start out in the state phi. You could have started out in any crazy state. As long as it has some non-zero overlap with the state phi, you can still get 1 with some probability. But you could also get 0, and then the physical interpretation of that is, no, we are not in the state phi. Okay, so again, the state before the measurement is what we've been calling psi, or what we called psi. And after the measurement, it's one of two things. It's either going to be phi if the answer to your observable was yes or 1, or it's going to be psi minus phi psi if the answer was no. Okay. So the reason all of this pertains to that problem is because in the problem I ask you, what's the probability if it's in one state to find it in another state? And this is just a formal justification in terms of the postulates of quantum mechanics that yes, we can find an observable that corresponds to that question, and this is how the observable works. It's just a projection operator. Okay. And so the probability can't spell, of getting 1 is nothing other than phi psi squared. Okay, and that's assuming again that these things are normalized to begin with. And by the way, if you get no and you get this state, that's not going to be normalized yet. You have to normalize it yourself afterwards. But that's not hard to do. Okay, any questions on that? All right, so we've been talking a lot about these, the translations and parity and things like that in the case of a one-dimensional particle, but of course we live in 3 dimensions, so I should say some things about how you translate all of this into 3 dimensions. And there's really not that much to it. You just have to sort of repeat everything 3 times, but we'll go over it anyway, just to make sure we understand how it works. So a position operator is now going to be a vector in 3-dimensional space, as opposed to a vector in state space. So in 3-dimensional space, the position operator is an x operator times x hat, a unit vector that's just a normal non-operator, plus y, the operator, times y hat, plus z, the operator, times z hat. Okay, and so x, y, and z, we could also write, if we want to give them an index, we could call them x1, x2, and x3. The reason that's useful is just then we can use summation notation over the indices. And we do a very similar thing for the ordinary momentum in 3 dimensions. P sub x, x hat, plus P sub y, y hat, plus P sub z, z hat. Okay, and P sub x, P sub y, and P sub z, we could also call P1, P2, and P3, just to sum over them. And so in particular, the commutation relations are that for any one of the position operators and any one of the momentum operators, you get I h bar, but only if the 2 indices are the same. So that's the Kronecker delta. That says if the indices are not the same, then you get 0. Okay, and any position operator commutes with any other position operator. That commutator is 0. Any momentum operator commutes with any other momentum operator. That commutator is 0. Okay, and so since the x's commute here, that tells us that we can try to make them into a complete set of commuting observables, and in fact, that works. So the set x, y, z is a complete set of commuting observables, right? So they are observables. They're Hermitian operators. They commute. And their eigenstates, this is the tricky part sometimes, their eigenstates have non-degenerate eigenvalues. In other words, if I tell you what the eigenvalues of x, y, and z are, then I've completely specified the state. And so the eigenvalues and eigenvectors are if I act with capital X on one of the states of the CSCO, I get back the number x, y, z. If I do the same thing with y, I get back the number y. And same for z. Okay, and then I can summarize all of this slightly more compactly by saying the vector position operator acting on my eigenstates of the complete set of commuting observables is the ordinary vector, not an operator, times the same thing back, where my R vector is a vector of numbers, not operators. Oops. So it looks like this. Now I'm going to sort of gloss over this in class and refer you to the notes to read more about it. But the states here, the eigenstates of position, are also can be called R, like so, corresponding to the eigenvalue that's appearing here. Or if you want to be even fancier about it, you can call it a tensor product. Okay, and the way you'd write this as a tensor product is x tensor product y tensor product z. Okay, the tensor product just means it's a way of creating a more complicated Hilbert space out of a Hilbert space you already know. So we know already how to make a Hilbert space for one-dimensional particles, and we've got 3 copies of them, and we just put them together to make a big Hilbert space that has all 3 of them. And the tensor product just obeys exactly all the postulates you would think an object like that would obey. So it just sort of obeys common sense things. And so most of the time, we won't bother writing it as a tensor product in this notation. The important thing to realize that it's exactly the same thing as just writing that. It's just occasionally, if you're interested in some mathematical property, the easiest way to prove it is using the tensor product language. Okay, so that's one complete set of commuting observables, but another one would be if you just chose the 3 momenta of the particle, the 3 components of the momenta. So this is another complete set of commuting observables. And depending on what problem you're doing, you might like to use them instead. One way to define them is that exactly similarly for x, p acting on the state little p gives back the number or the ordinary vector p acting on p. Okay, and so now we've defined eigenstates of position and momentum, and we can look back at what we did for the one-dimensional case and just write the corresponding formulas. So for example, R prime R is this time a 3-dimensional delta function of R minus R prime. And the same thing for the inner product of two momentum eigenstates. It's a three-dimensional delta function. Here, the three-dimensional delta function is the product of three one-dimensional delta functions. That's one way of writing it. Okay, and then the other thing we can do is we can write inner products like this, and we just get that by multiplying together three one-dimensional inner products. So we're going to get 1 over 2 pi h bar to the 3/2 times e to the I r dot p over h bar. When you multiply the exponentials together, it's the same thing as adding together the pieces in the exponential. Okay, and then you can write down three-dimensional wave functions like this, and three-dimensional momentum wave functions like so, and do things like completeness. So if we do completeness in position, we would say that psi tilde of p is equal to a integral over all possible positions. We're inserting a complete set of states, like so, times psi. And so now just plugging in what we got here, this is equal to 1 over 2 pi h bar to the 3/2, integral over all positions, e to the minus I r dot p over h bar. We took the complex conjugate of this right here, okay, and multiplied by the position state waves function. So again, completeness is what allows you to change position wave functions into momentum wave functions and vice versa. Okay, but now let's bump it up a notch and suppose that we have not one particle in 3 dimensions, but 2 particles in 3 dimensions. And later we'll generalize to the case of n particles in 3 dimensions. Okay, and how are we going to describe them? We're going to just make these states that are eigenstates of a complete set of commuting observables. So first we write down the complete set of commuting observables, which is going to be x1, y1, and z1 for the first particle, and x2, y2, and z2 for the second particle. Physically, that tells you exactly where the particle is. And so the eigenstates of that we can write in various ways. One way we could write it is by putting together the eigenvalues that describe it into 2 vectors. This means exactly the same thing as the state with eigenvalues x1, y1, z1, x2, y2, z2. Yet another way we could write it would be a tensor product of two one-dimensional, or sorry, of 2 three-dimensional particles separately. Okay, and so this component of the tensor product is acted on by only R1 and P1, and this one is acted on only by R2 and P2. And each momentum and position operator, that's a 2, just ignores the other component. It just does nothing. So what that means is, for example, R1, the operator, acting on R1, R2, the state, doesn't care what R2 is, so it just returns the ordinary vector R1, multiplying the state. Okay, and similarly for R2, acting on one of these states that are eigenstates of the complete set of commuting observables, it just gives you back R2 times R1, R2. Okay, and then you can write down all the commutators. For example, the important one is that R sub n commuted with P sub m, okay, is going to equal I h bar times delta nm if and only the components of R and P are the same. Which I could do by putting another index on it. Okay, so now the reason for doing all that is now we can talk about translations. So we want to write down a translation operator, for example, for a system of two particles. And the way we do that is we write the exponential of minus I a the vector dotted into P1 plus P2 over H bar. Okay, so this is a unitary operator. And instead of translating you in X, it's translating you by some arbitrary vector A. And so the properties that it obeys, acting on an eigenstate of the positions of the two particles, R1, R2, is it gives you back R1 plus A, R2 plus A. In other words, it just translates both positions of both particles by the same vector A. All right, and then furthermore, from the rules that we've worked out, you can find that if I do TA dagger R1 TA, I get back R1 plus A. If I do TA dagger R2 TA, I get back R2 plus A. And a nice consequence of that is that if I do this operation of translation to the difference of the vectors, okay, I just get back the same vector. So that says translations don't affect the difference in the vectors describing the positions of the particles. Okay, and then just for the record, if you do this to momenta, TA dagger P1, TA, that does nothing because the momenta always commute with each other. And so this just gives you back P1. And similarly for P2. Okay, so we have three operators here that are not affected by translations. We have the momentum of each particle, that's two of them, and we have the difference in the positions of the two particles. The sum of the positions of the two particles doesn't cancel because of the plus A. Okay, so that one doesn't count, but that gives us a way of constructing Hamiltonians that will be invariant under translations for multiple particles. And that's where we'll start with that next time. Okay, so last thing I wanted to do today would be to just go over the midterm. So let me share the different thing. This is actually on the web page now, but we should go over it in class, I think. Okay, so here's the set of rules or information for the midterm. It's on Monday. It's from 10 to 11 in 121 Davis Hall. So this is, I haven't actually been in this room, but I've been told it's a nice large room. This is the building that's next door to La Tourette. It's the building with the observatory on top. So that's where it will be. It will not be in La Tourette. Here's what you should bring and what you should not bring. So provided for you will be the formulas that you can find on my webpage for vector derivatives, vector and coordinate identities. You may, if you want, usually I hand them out before a test, but if you want, you know, in the age of coronavirus, you can print out your own ahead of time. That's fine. So bring your own copy of this if you prefer, or you can use the copy that will be available. You should bring something to write with and something to erase with. You should bring one standard sheet of paper with anything you want, but it has to be in your own original handwriting. Notice this has to be on paper. This should not be on an electronic device. You can use both sides of the sheet of paper, or actually I recommend that you just bring 2 pieces of paper with single-sided notes, anything you want. Also, you should bring blank paper of your choice for your answers. I don't recommend a blue book because what's going to happen is I'm going to be scanning these in. So it's better if it's loose leaf, and it's even better if it doesn't have the sort of raggedy edge that you get by ripping something out of a notebook. If you're worried about your papers getting mixed up with somebody else, it might be a good idea to put your initials on each page before the exam, just quickly doing that. So we'll make sure we've got the right papers for everybody. And then there should be masks that I think we're required to wear. So don't forget to bring paper, don't forget to bring something to write with, don't forget to make your notes. The way to make your notes is to start by going over all the homework problems and thinking of every concept or formula that you would need for those that you don't have memorized. Okay, no need to bring books, calculators, no electronic devices of any kind. You will not need a calculator. The test will be designed so that you don't need a calculator. And the notes should be only above. And then what to study, I think I've mentioned this last time, but start with the homework. You should also understand the postulates of quantum mechanics and how to use them. That was sort of the core of the class up until now. And so if you do study from the notes, studying the postulates of quantum mechanics is probably the best place to go. Okay. One other important bit of information is that the Sycamore County Circuit Court has decided that Monday might be a good day for me to have jury duty. So a lot of times what happens is when they find out you're a professor, they excuse you from jury duty. But that hasn't happened yet. Defense attorneys like to exclude professors for some reason. And so if they excuse me, which they may, then I will be there. But if they don't, then I am required to be on a jury. And so I will not be there on Monday. But if that happens, I will make sure there is somebody there to proctor the exam. So that's just a warning that I may or may not actually be there myself. Which is too bad because some of you I don't think I've ever met in person. Okay, are there any questions on that? Information for the midterm. Or anything else?
I have a quick question about the midterm.
Yeah.
Would you be able to tell us at all how many problems to expect, maybe?
So my current thinking is there will only be 2 problems, but they'll have multiple parts.
Okay, thank you.
One other thing I should say is that in the homework, a lot of people have been using computers to do integrals, which is fine. I have no problem with that. And I'm not going to give you any integral that will be super hard unless I also give you the integral itself. I'll give you maybe a list of integrals that might be applicable to the problem. But what you should be able to do is, for example, if I give you a definite integral, you should be able to recognize how that applies to a problem and manipulate it from the formula that you have into the integral that I give you. Okay, but I will give you any hard integrals that are necessary. So that's one thing. I think similarly, people have have been using computer programs to find eigenvalues and eigenvectors of matrices, which again on homework is fine, but you should be able to do that also on the exam. I might give you a 2x2 or 3x3 matrix that you have to you have to find the eigenvalues for and the eigenvectors for. Here's what I can promise you is I won't give you anything that, let's say it's a 3x3 matrix. I'm not going to give you a 3x3 matrix that involves solving a non-trivial cubic equation, because that would probably take you the full hour. So if it does happen that I give you a 3x3 matrix, the eigenvalue equation for it will be something that if you've correctly written down the equation, you should be able to recognize the roots of the equation very easily. Okay, so this is not my intent is not to give you problems where you're doing hard integrals or hard eigenvalue problems. It's to test the concept. Other questions? All right, so if not, I will stop the recording.